time?
We are. Okay, ready to go.
Okay.
Aloha.
Aloha.
Welcome to the first of our science activities series, monthly, every other Thursday, the second Thursday of every month. I want to first salute the only person I know who could bring Hawaii to us, including the weather, so easily, Nancy Mueller, and my co-chair, Judy Webster. So, and we have a fantastic committee. Nancy?
Okay, so they asked me on this committee to take responsibility for today's meaning of Astronomy FutureCast. We have with us two superstars, Dr. Alex Filipenko, and otherworldly astrophysicist from UC Berkeley, and a fellow otherworldly astrophysicist, Dr. Doug Simmons. Doug is the executive director of the Canada-France-Hawai telescope on Waimea, Hawaii Island. We will be shuttled into space among ideas far beyond our vision. Hold on to your Mai Tais, feel the liftoff, and enjoy the ride. Dr. Alex, to you.
Great, thank you. Thank you, Nancy. It's a pleasure to serve as sort of a co-host of this ARCS event. Being in the same field as Doug, I know him quite well. By the way, if all of you could just mute yourselves, that would be super, super great. And then we'll just have Doug speaking, and then we can have a Q&A at the end. But anyway, Doug and I actually overlapped at Caltech. He did his undergraduate work there, graduating in 1985. I did my doctoral work there, graduating in 1984. But Doug, I don't recall knowing you at that time, or maybe we knew each other, but it was a long time.
I remember you in the computer room in the basement.
You do remember me, okay. But see, you were just a lowly undergraduate at the time.
Right.
So
I wasn't authorized to speak to you.
So I wouldn't necessarily have noticed. But anyway, it's a fantastic institution, of course, in astrophysics. And then he went on to the University of Hawaii for his doctoral work, also a fantastic institution. After finishing there in 1990, he went for 4 years to the Canada-France-Hawai telescope, but then moved on to the Gemini Observatory, where he rose through the ranks and eventually became the director of the Gemini Observatory. Now, if you don't know, Gemini is a set of twin telescopes, 8 meters in diameter, one in Hawaii, one in the Andes of mountains of Chile. And they're an international partnership, including the US, and they provide the main really big telescope access to astronomers that aren't members of universities that have their own private telescopes. But then in 2012, Doug moved back to the Canada-France-Hawai telescope and is now the executive director. Now that's an amazingly important telescope. It's 4 meters in diameter. I was fortunate to do some work with it with a collaborator of mine in the late 1980s and early 1990s. But in my own field, one of the things that the CFHT is best known for is something called the Supernova Legacy Survey. It was a supernova, it was a survey of lots and lots of exploding stars. And it turns out that with these exploding stars, you can study the expansion history of the universe. And you can actually even tell that the universe is speeding up in its expansion. And although that discovery was made before the Supernova Legacy Survey with the CFHT survey greatly improved our confidence in the results that the universe is actually speeding up as a result of this amazing dark energy. Well, Maunakea has lots of great telescopes besides the CFHT, and Doug is involved in a lot of the operations and the work on Maunakea to keep it a thriving observatory. And I think that today he'll tell us about some of the wonderful work that has been done and what the plans are for the future. So Doug, go ahead.
Thank you, Alex. Appreciate it. I'm honored to be here with a nice introduction. The scariest part of this presentation is the switch off to screen share. So let me make sure I get that right. Hang on a second.
Looks
Okay.
good to me.
So we will start presentation. My presentations are kind of packed with videos and some audio. If the audio will allow, just turn your audio down locally if you can. I want to first of all start out with a little mahalo to ARCS, who provided me with a real boost many years ago. And what wasn't mentioned in Alex's little introduction there
Oh, wonderful.
for me was
the napkin for the small one.
Okay.
The host should mute everyone other than Doug at this point,
No, it's okay now.
whoever the host
Want
is.
to set it up and-
I'd love it. That'd be
Okay.
great. Thank you.
so these are all pictures of
You'll have to unmute Doug. The host has to unmute Doug.
Can you hear me now?
Yes.
Okay. So these are some pictures a long time ago, actually back in high school. My roots go a long, long ways back, building from scratch a pair of 8-inch telescopes. And though I'm director of big telescopes on Mauna Kea, at heart I'm still a astronomer who enjoys getting the little telescope out in front of the driveway and using it, particularly working with little kids if I can. Hang on. I'm going to drop out of screen share. For some reason it hung. Okay, try it again. So my story actually goes all the way back to Christmas morning when I was in 7th grade. And this is the only remnant of the first telescope that I ever had, which is a toy telescope from a company called Sears Roebuck. And that eyepiece I bring around in presentations all over the state of Hawaii as part of a program that I'll mention in just a second. And it's been an incredible thrill and a privilege and a pleasure going from a kid with a toy telescope to being able to operate and in some respects lead a pair of big observatories up on Mauna Kea. Essentially, Hawaii astronomy is my life's work. And I can't even begin to express how appreciative I am of the opportunities I've had as an astronomer in Hawaii. And I also want to express how appreciative I am to ARCS Foundation before I get into the actual presentation. As a graduate student at UH, it was over 30 years ago that I was awarded a scholarship. That particular scholarship essentially doubled my stipend that year. It was not a small deal at all. And it's in a number of ways inspired me to leverage my career in astronomy, particularly in terms of helping youth and STEM and other fields and sort of paying it forward. And that these days is mostly captured in our Mauna Kea Scholar Program, which I'm super proud of. We started it back in 2015. This is a program in which IFA graduate students, my alma mater, mentor high school students literally across all the islands, and they all have access to all the telescopes on Mauna Kea to do their research with. And as you can imagine, they do some pretty spectacular science fair work and senior theses, et cetera. And these little videos has been extremely popular and well covered by local media. And you'll be interested to note that you see where no girls have gone before. It's in particular been popular with young women who have really grasped the opportunity and run with it in a lot of ways. So with that as background, this particular presentation actually shown for the first time almost exactly 2 years ago. I've given a lot of presentations at Emilo Astronomy Center in downtown Hilo. It's only a few minutes where I live. And that's a beautiful 90-seat fully modern 3D projection system, wonderful sound, et cetera. So I had to kind of collapse it down into a 2D Zoom version, and hopefully it'll all work out okay. In any case, it's a slightly updated version of the presentation that
Thank you.
So I created that little video montage to give you a little teaser, if you will, of the topics that we'll cover over the course of this presentation. And I'll start it out with this sort of hybrid picture. In the foreground is a photograph I took of the mountain range in Alaska the last time I was up there. Beautiful plateau in the foreground and mountains there in the background. Of course, stitched in picture of a galaxy there. And if the story I'm about to tell you is considered that of a hike, along the path we're about to take are various milestones or markers, if you will, including black holes, whether or not there's life out there, first stars, and then onto the holy grails, if you will, dark energy. Do we live in one universe or a multiverse? And what is for me, and I'm sure for Alex and a lot of others, when are we going to get to the new physics? That's for me some of the most fascinating things on the horizon that I hope to see in my lifetime as we push the frontiers of astronomy and physics. So the question before us is, what discoveries might we expect in, say, the next 10 years in these various areas? I'm not going to cover them all. I don't really have time. But it's a talk that I thought might be interesting because it's sort of forward-looking and as opposed to necessarily a description of most recent research. To set the stage, I'll show you this picture, a highly colorized version of the Mount Wilson 100-inch telescope, which I was pleased to see survive the fires. By the way, I was watching that with a lot of angst not long ago. And it's actually the first big telescope I ever saw. I was 6 years old and living in Southern California. I remember seeing that incredible machine, though I did not know what a telescope was at the time. And the technology back then, of course, was quite archaic by current standards, using photographic plates, but the discoveries made with the Mount Wilson 100-inch were revolutionary, including the initial discovery that the universe is, in fact, expanding, as Alex pointed out earlier. And these days, the technology, give or take 100 years later, is just breathtaking. I'll put my Gemini Observatory hat on with the laser adaptive optics system that we've developed at both sites. And the imagery that you can create with these systems is absolutely spectacular. They have a reach into the universe that dwarfs anything we were able to do or accomplish back when the veritable 100-inch on Mount Wilson was first commissioned. And at that time, it was an incredibly powerful telescope. So predicting discoveries, you can imagine, is a little difficult, not easy, and marginally insane. In any case, I'm going to give it a shot with this presentation. And the means by which I do that is to basically look at trends going forward. Technology trends, as I said before, astronomy is an incredibly tech-driven field of research. And also trends in research and astronomy themselves, sort of mash them together to get an idea of what may be coming around the corner or so in, say, the 2020s in the field of astronomy. And the first area that we'll talk about is black hole research, which has undergone a tremendous amount of attention in recent years from various directions. This is the picture I stole from the movie Interstellar. I don't know if you saw it. I thought it started out pretty well, but ended in a different place, so to speak. Black hole, by definition, is pronounced that way according to the Merriam-Webster definition of a black hole. It's a region of space having a gravitational field so intense that no matter or radiation can escape. And speaking as a father with 3 kids in college, it's also a place where people or things, especially money, disappear without a trace. Black holes are mostly characterized by their mass, and they come in a variety of masses, extreme differences, including a number of black holes in our galaxy that have a few times the mass of our sun associated with them. You see an accretion disk and jets coming out of that black hole in the upper left. In the lower right is an animation of a quasar, and these are believed to have black holes perhaps as large as 1 billion times the mass of our sun. These are created through very different means. The top left black hole is created through the explosion of a star. The bottom right black hole is through the accretion, we believe, of large amounts of material in the early universe. So how do you get a black hole? From that matter, how do you get the end states of stars? I like this chart because it kind of captures everything in one shot. On the left, you see what we call a giant molecular cloud, a cloud of gas and dust. And kind of the nice thing about stars is that once they have a defined mass, their fate is basically written in the stars, shall we say. It is defined in terms of how long they will live and what their end state will be. Along the top track, you have the track basically followed by our sun, in which it's in that so-called small star state now. Eventually, it'll grow into a red giant. blow off its outer atmosphere, becoming a planetary nebula, and then the core collapsing into something called a white dwarf. And then on the bottom track, stars, say 3, 5, maybe 10 times the mass of our sun, go through a red supergiant phase, much larger than a red giant. Those are unstable and they explode, forming either a neutron star or a black hole, depending on fairly complicated circumstances. So those end states of stars, we've discovered over the course of the past many decades or so, and understand them reasonably well at this point. White dwarfs, that is the end state of almost all stars. About 97% of all stars end up in this white dwarf state. And that's a graphic you see there with the Earth to scale next to a white dwarf. So basically you've collapsed a star into an object about the size of planet Earth. The density is extreme. It's about 1 million grams per cubic centimeter. Remember, water is 1 gram per cubic centimeter. Diameter is about 10,000 kilometers. They only get up to about 1.4 solar masses. Beyond that, they become unstable. And they don't collapse any further, not because they have core fusion anymore, but because of the mutual electrical repulsion of electrons that are traveling very fast in that white dwarf structure. A little higher mass, and you get a neutron star made of something called neutronium, in which protons and electrons have been forced under gravity to merge and become neutrons. So these objects are way, way, way more dense. They're upwards of 10 to the 15th grams per cubic centimeter. Size is only about 20 kilometers. And I like to point out when I'm at Demi-Low, this is about the size of Mauna Kea, give or take, that you've collapsed a star into something that size. Maximum mass of order a few times the mass of our sun. And why don't they collapse any further? They're held up by the mutual repulsion of the neutrons in that star. And then if you get to even more massive stars, they do in fact go ahead and collapse to form what we call a black hole. The density, at least mathematically, they form a singularity. There may be sort of odd quantum mechanical effects that prevent you from actually forming a singularity. We just don't know at this point what's truly in the core of a black hole. The diameter is something called, actually the radius of a black hole is something called the Schwarzschild radius. That's the black bit that you see characterized there, also called the shadow of the black hole. And it's about 5 kilometers across for a black hole. It's about the mass of our sun. How big can a black hole get? There is no limit. It could be the entire mass of our universe over time. And as I said before, they collapse into what we call a singularity. So in principle, anything can become a black hole. It doesn't have to just be a star if you compress it within its so-called Schwarzschild radius. So what that means, if you could figure out how to compress the Earth into something about the size of a marble, it would become a black hole. And if you wanted to become a black hole, you'd have to be compressed into something smaller than a proton. So this is an incredible contraction of physical size to be able to shrink something into a black hole. And yes, there are microscopic black holes that we believe theoretically exist, but they, for various physical reasons, have very short lives. They evaporate away quite quickly after having been formed. So that's a segue to a chart that you've probably seen in one form or another in terms of what we call the space-time continuum that pervades throughout all of space. This is something Einstein was very famous for characterizing with his general theory of relativity. And you see the sun there, and below that is this sort of mesh, if you will, of representing the space-time continuum. And space-time continuum is curved in the presence of massive objects, in particular the sun. You see a little bit there from the Earth as well. And light, as it goes through space, follows the local geometry of that space-time continuum, and therefore actually travels not in a straight line next to the sun, but curves around the sun. This is something that was rather spectacularly demonstrated during a solar eclipse nearly 100 years ago that Einstein predicted. Also, time travels, or time occurs at a different rate depending on the strength of the gravitational field that you might be in at any given time. With respect to a relatively weak gravitational field, it gets slower and slower in the presence of a higher and higher mass object. So that's all relatively tame compared to a black hole. Black hole, all kinds of things happen. And light, it doesn't just go around a black hole. If it gets close enough, it actually falls in. It would have to have essentially an escape velocity faster than the speed of light to leave the black hole, and that is physically impossible. And in principle, time actually stops at the singularity in a black hole. So it's a case of extreme physics and a regime of intense research, because we're probing through black holes physical regimes that we can't possibly produce in the laboratory, and really push our theories of physics and astronomy to and occasionally through their limits. So black hole research has gotten a lot of notoriety lately, in particular in the two cases. This is a animation created by a team at UCLA led by Andrea Ghez. And what you're looking at is over time. The time is clicking off by year in the top right of this animation. And these are stars going around an unseen object right in here that is not emitting any light, but you can see the stars in its vicinity going around it and going through some fairly extreme orbital maneuvers, if you will, throughout this sort of 20 or 25 year animation. On the right, actually I got this from the 8-meter telescopes in Chile at Paranal. And occasionally, if you simply stare at this object with very high resolution images, you'll see it flash in the infrared. And that's due to material infalling into the black hole, getting superheated and flashing, if you will. So as a result of this research, and a lot of it done in Hawaii by Andrea Ghez, we have a high degree of confidence that there is roughly a 4 million solar mass black hole lurking in the center of our galaxy. So what's next in black hole research? Well, first of all, an update. If you haven't heard, that's part of the reason I wanted to emphasize this. This research just was awarded the Nobel Prize in Physics for 2020. Here's a nice caricature of Roger Penrose, who did a lot of the groundbreaking theoretical work on black holes. Reinhard Genzel, who's been working in Europe, and Andrea Ghez, there on the right, who has essentially dedicated her career at UCLA using the Keck observatories, which you see there, in fact, looking at the center of our galaxy, Sagittarius star, the black hole in the middle of our galaxy, when the twin Keck telescopes simultaneously looking at it. And this, there you go, you see them both pointing dead center at the black hole in our galaxy. And I'm sure Andrea was down in Waimea at that time using the Keck facilities to record the images that you saw earlier and were used to map the orbits of stars around the black hole in the center of our galaxy. Another area of black hole research that has gained a lot of notoriety, including in the area of physics prizes, is with an instrument called the Event Horizon Telescope. And this is a collection of radio telescopes scattered around the world. And what they do, you see a node here. This is actually in Hawaii and other sites, Chile and North America. And these facilities all concurrently look at the black hole in the center of our galaxy or in a nearby galaxy, record that information, and then it is played back and processed using supercomputers in Europe and the US to generate an image of what they found. In Hawaii, this technology is basically anchored at JCMT and a sub-millimeter array up on Mauna Kea. It's incredibly important sort of western leg of the interferometer in the Event Horizon telescope. So this telescope has ridiculously high resolution. As an example, if you were to use it and say look at a golf ball in Los Angeles from New York, you could see the dimples in that golf ball. It is just a completely different class of what we call spatial resolution in the field of astronomy. Some of the technical innovation required to make it work is the use of portable atomic clocks and data storage systems that are able to capture enormous amounts of data on big hard disks that are then flown to the processing sites, and the images are reconstructed from there. This was first used to show an image of the black hole in the core of the galaxy called M87 a year or two ago. That was named in Hawaii Povehi, and this is a project that I've been involved on for about 4 years or so, working with my friends at the University of Hawai Hilo College of Hawaiian Language Studies, Kahakaula. And we have developed a program called Ahua Hea Noa, which in Hawaiian means calling forth a name. And Hawaiian names to this are given to the great discoveries made from Mauna Kea. And it has been one of the most rewarding and interesting outreach programs that I've ever been involved with. And I think we're up to 8 major discoveries with Hawaiian names. So these are all new names captured in the incredible power of the Hawaiian language. And this is a little video that shows you Povehi, the name of this black hole given by a wonderful person called Larry Kimura at UH Hilo.
It's enormous, and its size is larger than our entire solar system. And that's what we're imaging, is that gas that's flying around at that close to the speed of light, and then it's the light produced by it bent by the strong gravity of the black hole.
It immediately, of course, takes me to this major documentation, the source of darkness, Kumulipo. Povehi. Po is this fathomless, powerful, ceaseless creation, darkness. Vehi is an adorning embellishment.
Povehi, as a name, is so perfect because it provides real truths about the image of the black hole that we see.
We look at it through the Hawaiian lens as genes, our genealogy. There is this connection between astronomy and this whole question about where we come from.
To be able to deliver the first image to the public of a black hole is really, really special.
Well, I'll share with you, I was privileged to see that image before it was released. It was highly embargoed. I was part of the team that developed the Hawaii media package, if you will, and worked with Larry and his team on the name. And that's one of those sort of once in a lifetime events where I actually had a hard time sleeping that night when it was so jaw-dropping for me to see something I thought I would never see in my lifetime, an actual picture of a black hole. And the fact that it more or less demonstrated Einstein was right yet again with general relativity was just another sort of tribute and hallmark to the genius of Einstein and the theory that still is kind of the bedrock in modern astrophysics and cosmology. So from here, what I call black hole research on steroids. And this is with a completely different type of technology. This is a computer simulation slowed down greatly of two black holes orbiting, obviously, and in the process of coalescing. In reality, when they're this close together, and they're several tens of times the mass of our sun, they're going around maybe 100 times per second. And you can see the sort of lensing effect around that as light is bent in the proximity of the black hole. Everything kind of shakes and wiggles, and eventually it settles down into forming a single merged object. So this particular research involves, as I said, a different machine altogether than a conventional telescopes. And this is a diagram that shows some of the early sort of coalescence discoveries of what we call LIGO, the Laser Interferometer Gravitational Wave Observatory. And what you're looking at is a pair of coalescing black holes merging to form a bigger one in this set of observations made early on with LIGO. So if you do the math on this particular object, it's pretty straightforward. The mass of black hole 1, there on the far left, has a mass of 36 times that of our sun. Black hole 2 is a little less than that. It's about 29 times the mass of our sun. So that adds up to 65, easy enough. The measured mass of the black hole that they coalesced to form was 62 times the mass of our sun, which begs the question, where did you lose 3 solar masses of material essentially in an instant? And what happened is that was released as gravitational wave, basically a wave propagating through that mesh of space-time I showed you a few slides ago, out in all directions. And that is so powerful that you can detect it with the technology in LIGO, even though these objects coalesced a billion light years away. So here's an aerial shot of LIGO, and I've been fortunate enough to be on a National Science Foundation panel to almost on an annual basis visit LIGO and basically assess and review their operations at their sites. And it is absolutely incredible technology that they have developed for these receivers. Basically, it's a two-arm interferometer. So there's a laser and this building right here that is split in half and goes through these two legs. Very special mirrors. This is an evacuated tube. That's 4 kilometers long. And the light is recombined through optical interference. Either it gets brighter or fainter as the gravitational wave propagates across this whole structure, expanding it and contracting it. So you see it as a brightening and slight fading of the recombined light in the interferometer in the system. So I would argue that LIGO today is even more important than Galileo's telescope of 500 years ago, which I, by the way, have seen in Florence, Italy, and that too is something I'll never forget. And I say that because in Galileo's time, there are lots of other telescopes. We're quite certain of that. Galileo was famous for using to look at objects in the sky. I would argue more importantly, not only just looking at the planets, but writing it down and publishing it. We got him into a lot of trouble, obviously, but that was an enormous contribution a long time ago. Today, there's really only one LIGO. There's another system in Europe called Virgo, but it's about 10 times less sensitive than LIGO. And it's this sort of window in time where we have essentially, kind of one telescope, one gravitational wave telescope, that we're creating an entire field of astronomy for the very first time. And it's very exciting to see what they have been detecting. Unfortunately, LIGO, like many other things, got shut down by COVID. They were in the middle of a fairly lengthy observing run at the time, and I believe they still remain shut down. So they're going through a lot of upgrades to the so-called quantum limit of the system. So with that in mind, my FutureCast for black hole research, watch for these emerging technologies, including in India. The Japanese are proposing to build their own gravitational wave observatory, and Europe as well, an even larger one. Look for cryogenic systems to be used to upgrade these to much higher sensitivity. Look for space-based gravitational wave observatories. An experiment called LISA that NASA has been sponsoring is a good example of that. And even more sensitive radio receivers used in the Event Horizon Telescope. And emerging trends to look for. First of all, now we have a picture of a black hole. What I'm pretty sure you will see next is a movie of a black hole. And that movie will be of the black hole in the center of our galaxy. I have some, quote, visibility into the EHT program through my collaboration with the telescopes here on Mauna Kea. And that's going to be just spectacular to see material spiraling and circling around the black hole in the center of our galaxy for the first time. Also taking a census of black holes in the universe for the first time. A lot of progress with neutron star physics, et cetera, as a result of this whole new sort of revolution in black hole research. Okay, next milestone marker on my little trail across Alaska there was first stars. And this is an area of intense research. Exactly when and how the first stars formed after the Big Bang is still a topic of a lot of research, theoretical and otherwise. The universe was very, very different back then, consisting almost entirely of hydrogen and lesser amounts of helium. So many of you will recognize at least the pattern, maybe not necessarily the details, of this periodic table of the elements. If you were like me, of my generation, you were forced in chemistry class to memorize that. I assure you, I can't remember the periodic table of the elements right now, but back in the first 300,000 years or so of the Big Bang, this was the periodic table. It's something even I can remember. It was hydrogen and helium back then. So those are the building blocks of the very first stars. After that, through incredibly chaotic and energetic processing, that hydrogen and helium created in the Big Bang got turned into essentially all the elements that you see fill out the periodic table from which we derive chemistry and life ultimately. So on the left, you're looking at a computer simulation of the formation of a galaxy, and what you're looking at is starlight in that. The term Z is a time metric. Z equals 0 is now. So it's going backwards in time to the present era. And on the right, what you see is the same thing, but in terms of dark matter and gas. And with that, you see the spectacular explosions that are occurring as that forming galaxy goes round and round and cannibalizes material, getting bigger and bigger in the process. The universe was a very, very energetic, very different place, shall we say, in that first early phase. And it's through this reprocessing over and over again that you get heavier and heavier elements until around Z of 0.6. If you watch on the left, all of a sudden, what was a chaotic galaxy is a spinning pinwheel, a spiral
Thank you
galaxy.
very much. It was wonderful.
And that is now the sort of the stable harbor that's required for the formation of life and planetary systems like our own. So very sophisticated models have been used to try and determine what those first stars might have looked like, what their properties might have been, and since they lack what we call metals in astronomy, it's a horrible definition. Metal means kind of anything other than hydrogen or helium. We believe they had extremely high masses, masses maybe 100 to upwards of 1,000 times the mass of our sun, which means they're incredibly unstable and had very short lifetimes. So with that as background, this experiment, which actually the results of which were announced just before the first time I gave this presentation, is really remarkable. And I've kind of lost the thread, but it caused quite the stir at the time. And this is a picture of a radio telescope. I realize it doesn't look like much, in the desert of Australia. And it was used to make a really remarkable discovery. So on the left, you see one of the classic sort of space-time diagrams with the Big Bang forming on the left-hand side here and time going off to the right. And it's actually in this area we call the cosmic dawn, when the very first stars after the Big Bang and after the so-called dark ages before stars formed came into being. And it's been the subject of intense research to push deeper and deeper into the universe to find these very first stars, some signature for them. And that's actually been done, we think, through a radio telescope, the radio telescope I just showed you, creating this particular spectrum, this absorption spectrum of hydrogen, intervene between us and those first stars. So I've got about a 2-minute little video, very nicely done by Nature magazine, that describes this spectrum on the bottom right, how the experiment was done, and what it means for research in the whole area of the first stars in our universe.
Scientists think they've made the first measurements from the cosmic dawn, the period in the universe's history when the first stars began to shine. But how can scientists study something that happened more than 13.5 billion years ago? Well, to understand that, you need to start with hydrogen. Hydrogen is a cosmologist's best friend. They use it to study everything. You see, a quirk of hydrogen is that it can emit photons as it switches between states. Specifically photons with a wavelength of around 21 centimeters. When astronomers point radio telescopes at the sky, they see a mess of different radio waves, but nestled in there is always that 21 centimeter line. These emissions from hydrogen have helped scientists to map the universe. It's how they discovered that we're sitting in a huge spiral-shaped galaxy, the Milky Way. But hydrogen isn't just useful for studying the universe today. Right after the Big Bang, the universe was a dark soup of electrons and protons. The particles soon clumped together as hydrogen, and after hundreds of millions of years, hydrogen collected into stars, generating light. Cosmologists call this the cosmic dawn. That primordial light is hard to see with a telescope because the tiny amounts of light made by the first stars would be extremely faint. So scientists have taken a slightly different tack. You see, when that light was first created, it changed everything, including the hydrogen itself, crucially making it able to absorb radiation at its favourite 21 centimetre line. With this in mind, rather than look for emission from hydrogen, cosmologists have looked instead for its absorption. They turn to the cosmic microwave background, the mess of radiation left over from the Big Bang. In theory, the moment light hit that early hydrogen, it would have started absorbing this radiation, and that should have left a blip in the CMB. And that, after decades of scouring for evidence from this time and 2 years of verification, is what cosmologists have found. But here's where it gets interesting. The signal they found is not at 21 centimetres anymore, because space itself is expanding. That line has stretched over time, which is handy for us, because the amount of stretching, the wavelength the light is at now, tells us how long the light has travelled, and so when those stars formed. Finally, this allows scientists to put some dates to the beginning of the cosmic dawn. But that isn't all. While the time the first stars formed seems about right, the signal is way bigger than cosmologists predicted. A lot more radiation was absorbed from this cosmic microwave background than makes sense given what we know so far about the early universe. something doesn't add up. And one tantalizing possibility is that we may be seeing the influence of dark matter. Now, this is far from confirmed, but if true, it would give us a wealth of information about dark matter's properties and where to look for it. So this little blip could not only give us a snapshot of the first stars, but it could be the key to unlocking one of the biggest mysteries in physics.
So here again is that radio telescope in the desert of Australia. This cost about $5 million, which sounds like a lot of money, but it's fairly modest still in the grand scheme of things for some physics and astronomy experiments. There's another experiment dedicated in large part to probing the very deepest recesses of the universe that will be launched, I think, in a couple of years. It's been delayed quite a bit over the past several years. This one costs about $10 billion. And this is something to watch for when it finally is launched. This, of course, is the James Webb Space Telescope, which will revolutionize in a lot of ways 21st century astronomy. It's an animation of the Ariane rocket that is going to be used to launch it from the European launch facility in northern South America. And this is, as I say there, a huge leap forward. It's a 6-meter class telescope that goes through an incredibly complicated set of steps to, in a sense, self-assemble a long way from Earth, what we call, I believe, L2. Unlike Hubble Space Telescope, which is serviceable, this machine is not going to be accessible once it's actually launched and deployed. And we anticipate, here actually is a full-scale mock-up of the JWST. You see that and the big solar protective sails underneath the big hexagonal 6-meter primary mirror there of JWST. We anticipate this being used to look in great detail at the very first so-called protogalaxies composed of some of the earliest stars that ever formed in our universe. So FutureCast for first stars anticipate a number of attempts to verify that radio detection that was captured in that little nature video. And I speculate if it is in fact verified through other research is the next step, kind of like we did with the cosmic microwave background, which is initially just uniformly isotropic across the entire sky until we developed the sensitivity to actually map it out with exquisite sensitivity and resolution. I speculate we'll be able to do that maybe with these observations of the first stars in the distant past of our universe. The big telescopes under design and construction now, including TMT and GMT and the ELT in Chile, will be used to look at the spectra of these first protogalaxies and in their own important way provide incredible research opportunities for these very, very distant, very first sort of luminous objects in the history of the universe. JWST will be used for a number of other areas of research in its nominal 5-year lifetime. And amongst those is in the last topic I'm going to cover, and that is in exoplanets, which is getting a tremendous amount of media coverage and interest in the general public. In this case, I'm going to emphasize a combination of technologies. One is a satellite that is in orbit now called TESS. You see the animation in the top left there, and it's doing an all-sky sort of panoramic survey looking for planets that are transiting, in other words, passing in front of host stars out to maybe a few hundred light years away. The idea is to use a combination of that satellite and ground-based instruments. One is at our telescope, Canada-France-Hawai telescope, I'll describe in a second, and to look for the so-called needles in the haystack. And so these are planets that we've been able to detect that we believe that are in transit across various stars. We believe we might be able to actually use JWST to perform exquisitely sensitive spectroscopy of a planet as it transits, you see in that animation, and to actually capture a record of the chemical composition of the planet's atmosphere, looking for what we call biomarkers, chemical substances that we believe are indicative of the existence of life on those planets. So this is a wonderful example of how space-based and ground-based technology is being teamed up to look for not just exoplanets and not just exoplanets that might harbor life, but actually to try and detect life on exoplanets that are within, say, 100 parsecs or a few hundred light years away. I'll zero in on our instrument Spiru. This is the latest to our complements of instruments at CFHT. We arrived about 2 years ago. It's an ultra-stable infrared, very high-resolution spectrograph that looks for the Doppler wobble and the motion of a star along the line of sight in response to the gravitational pull of a planet orbiting it. It's now in the early phases, what I'm pretty sure is the largest exoplanet survey ever conducted. It will get at least 500 nights of observing time at CFHT. And it uses, I believe, it's the first instrument to use a brand new generation of 4,000 by 4,000 pixel infrared arrays as well, which is actually working beautifully. And if it actually meets performance spec, which is about what we call a meter per second of resolution for motion sensitivity, in principle, if the models are right, you could actually detect a new planet every night with this system. This little time lapse on the bottom there you see of Spiru being assembled in our third floor ultra high stability lab at Canada-France-Hawai. And the top there, that's a news release of the truck that was used to haul it up after it arrived from France a couple of winters ago. So another update since I gave this presentation that I'm sure you've heard of most recently, and that is when it comes to biomarkers, the recent discovery of phosphine in the atmosphere of Venus caused an enormous amount of interest, shall we say, in the public and the scientific community. This little graphic shows Venus, of course, in the background. It's a satellite image of it. And in the foreground, these are the two sort of discovery spectra in white. This is the spectrum recorded at JCMT Mauna Kea, and in orange with the ALMA Observatory in Chile. Again, very fortunate. I was at lunch a couple of years ago at Haleakpahaku, the mid-level facility on Mauna Kea, and eating lunch with Jessica Dempsey, who runs JCMT, and she pulled out her cell phone and showed me a spectrum, that white one, for the first time. I had no idea what phosphine was or why it was important. It's not my field. And she said, you know, it shouldn't be there. There's no reason necessarily we understand how it could be there. And sort of by the process of elimination, there's considerable speculation that this little molecule, phosphorus plus 3 hydrogen atoms tacked onto it, is in fact evidence for microbial life suspended in the upper atmosphere of Venus that we weren't looking for before. This was quote, shot in the dark by a very talented researcher in England that found it on Mauna Kea, verified it in Chile, and triggered a kind of a tsunami of interest worldwide with the recent announcement that we had just a few weeks ago. You see the little meme I cracked up when I saw that, with NASA having a lot of attention on Mars over the recent years, and could be that the real superstar in the area of life nearby is actually in our backyard in the form of Venus. And on the far right, that's a sort of a mock-up of a potential balloon-borne instrument that could be deployed in the upper atmosphere of Venus to look for signs of microbial activity in situ. So the FutureCast for exoplanets, we have what I call a veritable armada of space and ground-based equipment that's been unleashed, a lot of it by NASA, but also by Europe and Japan and other countries. Wouldn't be surprised if we see this decade a mission to Venus, given the discovery of phosphine in its atmosphere. On Mauna Kea, with instruments like Spiru and others, like IRD over at Subaru, and other instruments at Keck, there's a tremendous amount of research going on to identify exoplanets that may actually have biomarkers in their atmospheres, if nothing else, just to measure what the chemical compositions of their atmospheres are. And I will stretch my neck out a little bit, but I honestly wouldn't be that surprised if, given the amount of attention, amount of effort, and my own sort of personal expectation, if we aren't in a generation that witnesses the discovery of exolife sometime in the next couple of decades or so. So let me bring it to a landing here with a few personal thoughts, starting out with Galileo. Again, the museum of which I was privileged to see in Florence a few years ago. On the left, this is the first picture we had of a solar system. It was a hand sketch by Galileo. So that's Saturn, Jupiter, and Mars, and along the bottom there, the crescent phases of Venus. And that was revolutionary for so many reasons, and of course was used to prove, really beyond the shadow of a doubt, that the Earth went around the sun and not the other way around. It took 400 years to get to the image on the right, which is the second picture of a planetary system. That was taken with Mauna Kea, a combination of Keck and Gemini. Those little white dots, these are planets. The host star is blocked out here by this white circle. And over time, in fact, we've captured movies that show them going around. It has been a long haul to get from the first picture of a planetary system to the second picture of a planetary system. And it's a tribute to the qualities of the site on Mauna Kea, the technology, the people, the perseverance to be able to pull this incredible technological feat off, to be able to take pictures, and not just pictures, but actually movies of planets going around nearby stars. So why is this important? Well, I kind of liken our age right now to be sort of a modern version of Lewis and Clark, or the Polynesian voyagers, mappers, if you will. Mapping and charting and becoming familiar with seas and lands that had not been explored before. By that I mean these stars that we are now exploring and finding planets around, I'm hopeful it won't necessarily be in our generation, but in future generations, these first exoplanets in our neighborhood, I believe, will be the targets for drones or robots with advanced propulsion systems. They'll have to be autonomous. They'll have to have a very long lifetime to be able to go and probe and then return and download their observations of objects orbiting nearby stars. But that's our role in our generation. We're the map makers. We're telling future generations where to point their incredible propulsion systems and rockets and robots that will be used, I believe, in future generations to explore the nearest stars and their planetary systems. So I'll finish with one last video of a hero of mine that really captures a lot of my sentiments and this presentation. Given the demographics of my audience, I predict you will recognize the narrator in this 2-minute video. He is a hero of mine and one of the reasons I got involved in astronomy.
We were hunters and foragers. The frontier was everywhere. We were bounded only by the earth and the ocean and the sky. The open road still softly calls. Our little terraqueous globe is the madhouse of those 100,000 millions of worlds. We who cannot even put our own planetary home in order, riven with rivalries and hatreds, are we to venture out into space? By the time we're ready to settle even the nearest other planetary systems, we will have changed. The simple passage of so many generations will have changed us. Necessity will have changed us. We're an adaptable species. It will not be we who reach Alpha Centauri and the other nearby stars. It will be a species very like us, but with more of our strengths and fewer of our weaknesses. More confident, far-seeing, capable, and prudent. For all our failings, despite our limitations and fallibilities, we humans are capable of greatness. What new wonders undreamt of in our time will we have wrought in another generation and another? How far will our nomadic species have wandered by the end of the next century and the next millennium? Our remote descendants, safely arrayed on many worlds through the solar system and beyond, will be unified. by their common heritage, by their regard for their home planet, and by the knowledge that whatever other life may be, the only humans in all the universe come from Earth. They will gaze up and strain to find the blue dot in their skies. They will marvel at how vulnerable the repository of all our potential once was, how perilous our infancy, how humble our beginnings, how many rivers we had to cross before we found our way.
That little video, which is quite famous from Carl Sagan, it's called The Frontier is Everywhere, and includes some really quite spectacular videography and imagery. And I've used it on multiple presentations and always find myself in a bit of a chicken skin mode when I hear his voice again, thinking back to PBS and Cosmos and staying up late as a little kid to watch that whole series and hear his remarkable views and voice on astronomy and how we fit into a bigger picture. As I alluded to at the beginning of this presentation, I feel incredibly blessed to be part of a team of astronomers and engineers and administrators worldwide. It's not a huge team. When you add us all up, it's a fairly small community in astronomy, and we are fortunate to be able to practice our art, if you will, from the summit of Mauna Kea, and fortunate to be able to sort of lay our layer in the foundation of knowledge and understanding, exploration, and discovery that future generations will depend upon, just as we depend upon the layers and foundations that were set in place long before we got here, like by people like Galileo and Newton and Kepler, etc. And I think about that as I look up into the night sky with my little homemade 8-inch telescope, which, by the way, is sitting about 10 feet to my left in my bedroom right now, that I made back in high school and still works spectacularly well. So with that, a few closing thoughts to share with you as I button up the presentation. First of all, defying all odds, we likely exist in an infinitely large realm when I look at the entirety of the information available, and that means that we are infinitely small, and I'm fine with that. It means that we now at least have context for where we fit into that big picture. Through our determination and intellect, we're beginning to map our place in our vast home, helping satisfy our insatiable need for context and meaning. We're on the cusp of learning if we as life forms are common or as rare as existence itself. And that's a whole nother presentation where I get into the layers of existence. And finally, we each ride a wave of life that crests in our time. The wave we are riding now is unlike any our ancestors encountered. And my closing advice for you is enjoy the ride. So with that, I'd like to share my mahalo and aloha to a wonderful audience. It's a little awkward compared to being live with you, which I would much prefer to be able to have sort of feedback that's useful for these sorts of presentations as I run through the credits here. I appreciate the opportunity to share a few thoughts about modern astronomy, what we're doing from Mauna Kea, and the path forward that I think is just around the corner in a number of areas of really remarkable research. So with that, I will come out of share mode, and I'm happy to take a few questions if you would like to do that.
I'd like to just start by thanking you, Doug. This was unbelievable. I don't think I've ever been to a presentation as buttoned up, informative, interesting. We couldn't escape for a moment. Thank you so much. So now we will continue with the questions, but I'm blown away, and I'm very proud of what you've done for us. Thank you.
Appreciate it. Surely you have questions. And if I don't know the answer, Alex does.
Well,
all the hard ones go to him.
I have a question because I go to Hawaii. I have a little place over there, and I know that there's a great problem with the indigenous people and access to the Mauna Kea and the future of the Mauna Kea. What's going on there now? Are is your work going to kind of seamlessly continue, or is there worrisome in the balance?
Yeah, so this is my life, Nancy, anymore. I was at the TMT groundbreaking October 7th, 2014 on the summit, and that event, I didn't know it at the time, changed my life. And by that I mean, I spend about half of my time not running an observatory, but in the community, including the Hawaiian community, with a whole variety of projects, programs, and collaborations going on. So the TMT has got a lot of attention given the controversy surrounding that. What I've actually been focused on is what we call the master lease, which is the agreement that all of the existing telescopes rely upon to be renewed if there's going to be a future for Mauna Kea astronomy. And I won't get into the weeds very far, but we have sort of 5 or 6 years to have that renewed, or things are looking pretty bleak for the future of the Mauna Kea observatories. I personally believe that there will be a future, and I wouldn't be doing what I'm doing if I didn't think it was going to end well in some form. I hope that this is an opportunity to kind of do a reset, and not just for Mauna Kea astronomy, because it's this new master lease. It'll take us to basically the end of this century, right? And a lot's going to happen this century. Even if we don't get TMT built this time, in that time, so much could happen. You could easily have another TMTs coming along. And I hinted at it, but again, some of the most rewarding work that I've done is partnering with the Native Hawaiian community through programs like Ahuahea Noa, the physics of Po, which is Uncle Larry and I think we have over 1,000 people we've shown that to, including the Hawaiian Convention Center. And understanding and respecting each other and meaningful and human ways is the starting point in this collaboration. So I personally would very much like to see, and what I'm trying to pursue is, in fact, not an endless pile of litigation going back and forth. That doesn't really solve anything, in my opinion. There has to be a mutual, not just respect, but admiration, if you will, for what we all bring to the table within the Hawaiian community and all aspects of the people of Hawaii. And that is very much what I'm focused on. So I think we'll get there. But the next 5 years, Nancy, I cannot begin to describe how important they are for 21st century astronomy. In the Northern Hemisphere, most of the action's in Hawaii. In the Southern Hemisphere, it's mostly in Chile. That's just the way it all the investment worked over the years. I said it before, Hawaii astronomy is my life's work, and I'm throwing everything I've got. There will be nothing left on the field from me by the time we get to the next 5 or 6 years.
Alex?
Oh, I see that Heidi has her hand up. So do you want to go ahead and unmute, Heidi?
Yeah, I was actually going to ask about the exact same question, because I also have a home in Hawaii, and that's very interesting, Doug. And I just pray you can find some kind of an answer, because it's so important for so many people, including the Hawaiians. I mean, it is. And it was a marvelous presentation. I absolutely loved it. So thank you.
My pleasure.
There's some questions in the chat box, one from Joe Whitehouse. Could you comment on the importance of collaboration with indigenous people and with global scientists? And she was blown away by the way the black hole photo emerged.
Yeah, so that program started with Native Hawaiian Kupuna elder who approached me back in 2017 with this, what he thought was an idea that would be soundly rejected, which was to start naming, and if possible officially naming, discoveries from Mauna Kea. And in Hawaiian culture, through the Kumulipo, which is the most famous creation chant, I've had the really wonderful experience working with Larry Kimura, Dr. Kimura, who, if you're not familiar with him, Larry is in Hawaii generally attributed with saving the Hawaiian language, Alela Hawaii, in the 70s, which at that time only a few hundred people spoke, and now it's several tens of thousands. And he turned it around, and as you can imagine, saving the Hawaiian culture would be impossible if we didn't save the Hawaiian language. And I find it personally really cool when I was in airplanes, now I'm grounded, or standing in lines in the supermarket to hear Hawaiian spoken. I don't speak it myself, I know a little bit, but it's through my collaboration with the Hilo Hawaiian Studies program. Just wonderful, very warm people that I've learned a lot, and we've grown quite close through that collaboration. And part of the secret to the success was this wasn't the idea of the astronomy community. This was Hawaiian Kupuna who had an idea and reached out to the astronomy community. Can you make this happen? And I immediately embraced it. I told John, don't worry about the IAU. We're just going to name things. and when the media picks it up, there are no rules for naming black holes. We're just going to do this. And once it's in the social vernacular, if you will, there's no going back at some level. Like I said, I believe we're up to 8 discoveries with Hawaiian names. Dwarf planets and several asteroids there, in fact, have been officially recognized by the IAU, where there are a variety of rules. And I, in fact, see kind of a revolution in the International Astronomy Union and their whole naming system as a result of what's occurring with the revolution in Hawaii to assign Hawaiian names from a Hawaiian program to Mauna Kea discoveries. And, when I talk about this in public, I liken it to the sense that Mauna Kea now has a voice, and that voice is Hawaiian. And it's heard all around the world. That Venus story that I showed you, the aggregate readership, I looked at the stats, was over 15 billion. That means many, many, many people read it more than once, right? That's many times the world population. Povehi was almost as large as that. So we're getting incredible amplification through this collaboration of the Hawaiian language throughout the international community. And it shows you how astronomy and Olelo Hawaii and the local community can work together to save the Hawaiian language. And
Joe, follow us up with how can we, the women of ARCS, help you achieve these goals?
Prayer is good. I think that a certain amount of just respect for the complexity and nuances of working in the community here. I see the reports, distant from the mainland, and they tend to, unfortunately, pit this, science versus culture thing, which is a complete mischaracterization. Hawaiian science is riddled with incredible accomplishments when you look at centuries of Hawaiian achievements, like fish ponds, for example. If you're not familiar with that technology, that was used for like 1,000 years and fed a population of Hawaiians that exceeded the population that are here now. There's well over 1 million native Hawaiians pre-contact. And the fact that they would, for example, use the color of flowers and trees around fish ponds to gauge the pH in the water as a metric for determining when it was appropriate to bring the fish in. Now, they didn't know about pH, but they were incredibly observant scientists, in my opinion, and engineers to develop fish pond technology that allowed them to, like I said, feed with other technologies over 1 million people. It was just spectacular what Hawaiian science did. Recognizing, acknowledging, and appreciating science in all its form, including indigenous science, is crucial. I generally liken, Hawaiian cosmology and the other cosmologies as basically layers, if you will, in the history of the human story. Today's story is the Big Bang. And as much as I am a proponent of that and believer in that, I also believe in 1,000 years, the Big Bang will be completely replaced with something else. And in 1,000 years, people will look at all these cosmologies and all these stories. One of them will be the Big Bang. And all of a sudden, you'll see how it's a tapestry. It's not one is better than the other. One builds into the other. And therefore, they are all important and should be respected.
So speaking of tapestries, Linda Millard says that she's fascinated by the comparison of our neural networks and the early galactic clusters.
Yes, that whole technology, for example, sort of AI or machine learning, for example, is really catching on, as you know, Alex, in astronomy. And in fact, we're using it for a couple of applications in advanced data processing at the Canada-France-Hawai telescope. I noticed a news release by the University of Hawai, I think it was just yesterday, of an enormous three-dimensional map, if you will, of the universe, created through a combination of observations made with Pan-STARRS, which is a pair of telescopes on Maui, and machine learning using observations of galaxies, I think several hundred million through spectroscopy. And basically they trained the computer with those galaxies in how to identify the distances of other galaxies, and we're able to create a three-dimensional map of the universe through that really advanced use of computer technology. So neural networks are, it's exciting, amazing, and scary at the same time. The way these things are able to catapult you into sort of research regimes that weren't necessarily possible even 10 years ago.
If you'll permit me to make a comment or ask a question regarding the phosphine, first, it's just one feature, so how do we know it's phosphine? And second of all, just so that people don't get the wrong impression, astronomers are not yet saying that they've definitively found life on Venus, okay?
Yeah, right.
There's a lot of controversy, not necessarily about the detection, but about the origin of the phosphine and whether it requires a biological process or can be produced by abiotic chemical reactions.
That's exactly right. Yeah, it's kind of a process of elimination. We can't figure out anything else, which is not necessarily a good way to claim a discovery. So right now, as you can imagine, the race is on to look for other phosphine lines. I will say we've already done a discretionary time at CFHT, and I'm waiting anxiously for the results in the near infrared to confirm phosphine. There's only one absorption line, and that was a criticism of the research. On the other hand, you see the sociology, if nothing else, and the intense curiosity of the world's population and these sorts of truly basic questions. Like I said, I stuck my neck out a little bit, but between the research going on Mars, Enceladus, the Jovian satellites, now Venus added to the list, there's so much intense research going on that I would not be at all surprised if there isn't some sort of microbial life detected elsewhere in the solar system. And at some point in time in the future, if we don't find it, it actually opens up for me an more interesting question: is that why are we alone? For me, that's even more troubling.
Well,
why do we have company?
We passed through the great filter and no one else did.
I don't feel that lucky, Alex. No, we cannot be held responsible for the only form of life in the universe. That's too big a responsibility for me.
Are there other questions, either people with their hands up or in the chat room that I'm monitoring here? There's a lot of people giving you kudos, basically, Doug, on an excellent talk.
I ask whether their little microscopic black holes are found inside of cells. Does anyone have any biologists?
No, not certain, haven't heard about that. I made a reference to that. There was speculation, and Alex, jump in here, when a super collider called the Large Hadron Collider was first going to be turned on. It's in Europe, and was used to detect something called the Higgs boson, another physics Nobel Prize therein. And I think, in fact, there was a lawsuit, wasn't there, to try and prevent that particle accelerator from being turned on?
There was. It was spearheaded by a dude in Hawaii.
Is that right?
Yeah.
I didn't know that detail.
Oh yeah, Hawaii apparently is very open to all kinds of frivolous lawsuits.
All types of litigation. The lawyers make a lot of money in Hawaii.
Yeah.
So theoretically, you can produce them. They evaporate through something called Hawking radiation. Stephen Hawking predicted it very quickly. But to my knowledge, there has never been any proof of them existing in the form of a direct detection. And Alex, correct me if you're wrong.
Yeah, no, that's correct. There's no direct detections of evaporating black holes. And regarding ones that are small enough to be inside cells, those would have evaporated and basically ceased to exist long, long ago. So So they don't really exist. The ones that might have been produced by the Large Hadron Collider that would then destroy the world, that was a bunch of hogwash, in my opinion, because we see energetic charged particles called cosmic rays in the universe that have much, much greater energies than those energies produced by the Large Hadron Collider. And those cosmic rays occasionally, collide even inside Earth, and they haven't produced black holes that have devoured Earth. So it really was only a tiny, tiny chance that this was any risk whatsoever.
It proves you can sue anybody about anything at any time.
That's right. There you go.
So Doug, there's another question in chat from Joe. Is the lysosome the cellular equivalent of a black hole?
I have no idea what a lysosome is, sorry. Alex, do you know the answer to that one?
No, not really. I mean,
I'm pretty sure the answer is no, but.
Where
you want to elaborate, Joe?
Nothing, not even light, can escape.
Right.
Whereas a lysosome is a component of a cell, but I'm not exactly sure what the function of the lysosome is that would make it analogous to a black hole.
I think it's a Susan Equistapaci question.
Lysosomes are kind of the garbage dump of the cell. Things do disappear into them. But I think the analogy might stop there.
So like the money that I'm paying to send my kids to college. Yeah, a sociological black hole.
Oh, goodness.
Thank you for these tantalizing ideas. I'm admiring of anyone who can even contemplate something as large as our universe. And astronomers and cosmologists are wonderful. So,
And I just want to express incredible gratitude for the collaboration that you've established with the elders of the Hawaiian culture. I really feel that this is an important partnership between science and technology and the people who, started us. So really, really grateful for that collaboration.
It's a whole other presentation, and I've said on many occasions, I believe that the future of Hawaii astronomy lies in Hawaiian Kupuna. They see the big picture. They understand the importance of all of this to their grandchildren, and it's a matter of respecting and honoring and enabling a path forward consistent with their vision that I think can beautifully mesh or meld, if you will, with contemporary science.
Yes, and I guess it's been more of a problem at Maui, so I'm glad to hear some collaboration.
Yeah, there are challenges on every island,
Okay.
But in any case, our work with Kahakula has been, like I said, really, really a lot of fun. I look back at all the community projects that I've been involved with. That's the keeper.
Well, are we ready to go to dinner or?
One question for you, Nancy. This, I unavoidably was detained and couldn't join. Has this been recorded so there would be the option to watch it later?
You will all get an email
with
the recording as soon as it's humanly possible in our time, not galactic time, to get it to you. I would say sometime next week you'll have it. It's just a matter of the process, but it will all be the same. You'll see the whole thing.
Thank you.
Yeah, it's thrilling. Doug, again, thank you so much. Patty, thank you so much for your help. Alex, thank you for stepping in and moderating this. It was a pleasure having you again with us at ARCS. And all of our attendees, all that were involved and were here, thank you for coming. It takes a village.
Nice.
It was a pleasure to do this and a pleasure to have this. I'll be dreaming about this tonight. Thank you.
Thank you, Nancy.
All right,
Thank
aloha,
you.
everybody.
Incredible presentation. Yes.
Aloha.
Okay, aloha.
Aloha. Aloha.
Oh, goodness.